There's this incredibly powerful, relentless force at work all around us. It's in the pipes in our homes, the cars we drive, even the monuments in our cities. It's a kind of unseen enemy we're fighting every single day. And today, we're going to pull back the curtain and take a good hard look at it. We're talking all about corrosion. So let's kick things off with a little puzzle. What on earth could a browning apple possibly have in common with a huge, crumbling steel bridge? I mean, one seems like a simple organic process, right? The other is just a massive failure of engineering. But what if I told you they're both victims of the exact same fundamental chemical process?
Well, the answer to that question is corrosion. It's this silent, sneaky process of decay that's happening everywhere. So let's get into it and break down what's actually going on.
At its core, you can think of corrosion as nature just trying to hit the reset button. See, we spend a ton of energy digging ore out of the ground and refining it into these strong, shiny, useful metals. Well, corrosion is just the natural chemical reaction of that metal trying to go back to its original state, back to being a more stable ore. It's a constant one-way journey back to dust. Okay, so that's the big picture view. But to really get it, we've got to zoom way in and look at the chemical culprits that are doing the dirty work on a microscopic level. I want you to imagine every single piece of corroding metal as a tiny, self-destructing battery. Seriously, it's got three key parts. You've got the anode, which is the part that gives up its electrons and literally falls apart. Then you have the cathode, which is the part that accepts those electrons. And finally, the electrolyte, which is usually just water, that acts like a highway, letting the electrons travel between them. As soon as that circuit is complete, the decay process kicks into high gear.
It's almost like our recipe for destruction, right? To get rust, you only need a few simple ingredients. First, you need that anode and cathode, which can exist on the very same piece of metal. Then, you add an electrolyte, like water. And for the final touch, you need an oxidizing agent, which is usually just the oxygen floating around in the air. Mix them all together, and that chemical reaction is pretty much inevitable.
But here's the thing, not all recipes are created equal. While regular freshwater is a perfectly good electrolyte, salt water is like a supercharged, high-performance version. The salt ions in the water create this fast lane for electrons, speeding up the whole process a lot. This is exactly why ships, offshore oil rigs, and even cars in places that salt their roads in the winter rust out so much faster. The salt is literally turbocharging those tiny destructive batteries.
So, that's the nitty-gritty science of it. But why does this matter so much? Let's zoom back out for a second and look at the absolutely massive ripple effect this tiny chemical reaction has on our entire world. This process isn't just an eyesore. It comes with some staggering hidden costs. We're talking about the economic drain of constantly having to repair bridges, pipelines, and buildings. We're talking about the serious safety risks when critical structures or equipment fail catastrophically. There are huge environmental disasters when corroded tanks leak nasty chemicals. And, we're even watching the slow erasure of our own history as public statues and monuments just crumble away. If you really want to put a number on that economic cost, well, you might want to brace yourself. The world spends an estimated $2.5 trillion fighting corrosion every single year. To put that in perspective, that's over 3% of the entire world's GDP, all of it spent just fighting a simple chemical reaction. It's an absolutely mind-boggling amount of money. A materials scientist once captured the scale of this fight perfectly. They said, humanity is in a constant multi-trillion-dollar war against a fundamental law of chemistry, a war we only fight to a standstill. And that's the real key here. We can't actually win this war. The best we can hope for is to manage the battlefield.
But we're not totally helpless. Don't worry. Over the centuries, we've come up with some incredibly clever and ingenious ways to hold back the rest. So the question is, how do we fight back? We've basically got three main lines of defense in our playbook. The simplest one, just create a physical barrier. Think about the paint on your car. It just keeps the water and oxygen away from the metal. Then there's a much cleverer method called galvanizing. We coat steel with a layer of zinc. Now, zinc is more reactive, so it basically sacrifices itself, corroding first to protect the steel underneath. And finally, for huge structures like ship hulls or pipelines, we use something called cathodic protection. This uses a small electrical current to trick the entire structure into thinking it's always receiving electrons, which stops that corrosive circuit from ever getting started. Pretty cool, right?
So when it really comes down to it, this whole battle against decay isn't about finding some magic bullet to win outright. It's all about intelligently managing a process that is never, ever going to stop. The real goal is just to choose the right defense for the right situation so we can extend the life of everything we build. And all of this brings us to one last really fascinating question to think about. We've spent our entire history fighting corrosion here on Earth, where it's basically nature's default setting. So what happens when we try to build a sustainable future on a place like Mars, with its own completely unique and incredibly harsh environment? How do we fight decay on a whole different world? Well, that's a challenge for the next generation of engineers to solve.